So basic chemistry concept. This is the topic for us to discuss. All right. And you will be happy and you will be surprised of actually how much you already know about basic chemistry. This will be very much similar to that what you have learned from your. I didn't turn on my camera. Let me turn on the camera. All right. Okay. I'm much energetic now. So you'll be surprised to know how much you already know, and it is very much, I mean, many of the concepts are very similar to what you have learned from your school, high school as already, right? So the question might be some, I mean, arising from you that why I have to learn all these things we have already know. And at this point, I congratulate you that if you remember and you know many of these, but for your information, just to facilitate the transition of our learning into chemistry to much depth information, much depth concept that we will be learning from the later weeks. Some of our friends here, they probably have forgotten or they have not that much understanding. So I want to take everybody on the same boat, all right? All of them on the same stage, and then we move forward. So if you have forgotten, don't be shy, don't be scared, just ask the question, and I love to hear from you. And actually this is I mean, one of my pleasure, since it is an online learning now, I cannot see your face. I miss those things actually. When in the class I used to see your face and then I can talk to you guys, and I mean, looking at your face is so much, I mean, nice to environment. It makes the environment nice. Since I cannot see you, I would like that you voice up, you talk, so that at least I feel that I'm not talking to myself. Yeah. All right. So learning objective for it today is what is an average atomic weight? We know that everything has a weight, right? Atoms. Everything that is made up of atoms, the atom itself has a weight, and weight, and this weight surprisingly is not the similar that we know that atom has the weight. What we know the atom has the weight of an atom is not exactly the weight of that atom, but average of all that same type of atoms. All right. So the average thing, why the average thing is coming now? What does it mean? And if we go to describe about the average atomic weight, the isotopes are coming in here. So what is the isotope mean then? Since there is the isotope, we have to consider the average atomic weight. We will be discussing about it. Empirical formula and molecular formula. We know that H2O, right? Who doesn't know H2O? H2O is water, we know. And some of us, our friend, they type it the ethanoic acid. CH3CH2OH is the ethanoic acid. We know that. Sorry, CH3COOH is the ethanoic acid. So we know this thing. And what is it? Is it an empirical formula or a molecular formula? And if it is a molecular formula, then what is the purpose of empirical formula? And from empirical formula, how can we go to the molecular formula? Those things we will be discussing. And later on, we will know that a bunch of atoms or bunch of molecules, if we put in one pot, one place, we cannot just say that, okay, there are 1 million atoms there or 5 billions of molecules there. We have to describe it in some understandable or fathomable that we can relate to our concept terms. And that term is moles, that everybody understand, the moles, and it is coming from the mass, the number of particles that we will be describing into. And those particles that consist of atoms, molecules, ions, and all those things, all right? Later on, the volume of gases will come, and it is very interesting, the volume of gas, and from the volume, because gas is everywhere, right? I'm inhaling, and I'm inhaling the gas. Of course, I need oxygen, but that is much detail. I'm not going to detail, but we inhale oxygen, right? Other things are coming in. But that oxygen, I cannot say that, okay, I have inhaled 10 molecule of oxygen. We cannot say in that way. We have to come out in terms of that this much volume of oxygen I have inhaled. So in this volume, at this temperature, at this pressure, at this condition, how many moles can be there? Of course, it is a calculation, a concept. It is not exactly the same, but we can understand, or we can find a very precise, almost very precise idea about how many number of moles or molecules or particles or atoms are there. So this is why we have to understand what is an atom first, because everything is made of atom, right? Have you ever seen an atom? Anybody? No. Nobody has ever seen an atom?
Like the structure, but it's not 100% accurate, so no.
Okay. Okay, that's good, Munir. It's not 100% accurate. I appreciate your honesty that, yeah, it's not 100%. Whatever we have seen, the picture or the 3D model on the internet or YouTube or books, photos, yeah, it's not 100%. And I appreciate Pupathi's Raja's comment here. I don't have superpower. Yeah, none of us has a superpower. But the interesting thing is, we are all made of atoms, isn't it? Do you agree? We all made of atoms.
Yeah.
So when you are looking at me, you are seeing a bunch of atoms, isn't it?
Yeah.
Yeah. So I am atom. I'm not atom, one atom, but I am a stack of a bunch of a trillion quadrat. I don't know the unit. Many atoms. Interesting thing is, this atom at individual atom looks totally different than when they are stacked up. That is a very interesting thing, and that is something that it requires some other advanced higher level of knowledge. But to go to that higher level of knowledge, we must start from this one single atom, right? And that is why I'm going to this one single atom now. So it is very, usually we illustrate it as a sphere. An atom is a sphere, right? But something that is hard to conceive, that this sphere, that spherical thing, the atom size, is not a solid. There is no boundary. We just conceive that this is a boundary. There is an atom, there is a round shape, spherical shape, but there is no physical boundary of that atom. But although we understand, when we express it, when we show it, when it is the 3D model comes out, or the photos like here, you see there is a sphere. And in that sphere, at the center, there is a very dense, very heavy, enormously heavy, dense space that is called the nucleus. In that nucleus, whole the mass of that atom is there, is concentrated in there, because there are protons and neutrons are there. Both of them are particles, different type of particles, proton is positively charged particles and neutrons are no charged. They are totally neutral. They do not carry any charge. You may ask me why it is positively charged. I don't want to go into detail, but it has to be doing something with its rotation or the orientation. All right. Okay. Just understand that at the center there is something very heavy, very heavy. And when I'm saying it's very heavy, it does. I mean, we do not say it's 100 kilogram is here, not in that sense. But given the size of an atom, in relation to the size of the atom, it is very heavy there. All right. Sorry. Okay. And then the surrounding thing of the atom, there are some other type of particles. And that particles are called electrons. All right. The electrons are surrounded in the periphery of the atom. Of course, in different level, the electrons are in different levels around the nucleus, and these electrons, due to its rotation and movement, they are negatively charged. So electrons are negatively charged and protons are positively charged. The interesting thing is that the value of the charge, negative charge and positive charge, although they have the one proton is 1,800 times or more than that times heavier than an electron. All right, but the charge, the value of the charge is same. So if they have one, let's say that electron volt actually. So one electron, the unit of the negatively charged is equal to the 1 unit of the proton positive charge. Although one electron and proton, there is a huge mass or weight difference, but the charge is same. So let me take some pencil, yeah. All right. So these protons, this nucleus is here staying, and the electrons, since they are positively charged and negatively charged, this electron does not go out from here. It does not go out of that. They have, because there is a different opposite charge, they have an attraction between them. Right, there is attraction between them, and that is why the electrons does not go out of the boundary. Let's say this is the boundary, and this boundary, conceptually we say that okay, this is imaginary boundary and this boundary is shown as a sphere. Okay, and now these electrons are floating around this nucleus. And of course, the nucleus is proton and electrons, and the electrons are floating around it. The electrons, usually we show in the classical structure of atom that this is, here is the nucleus and the first orbit of electron, second orbit of electron, third orbit of electron, but in reality, it is not the case. Of course, there is a difference in orbit, but this electron here, it does not always stay here. It can goes up to here and then come back to here and then goes up to here, come back. So in this way, they move, but they stay within that boundary. All right. So, okay, I think it is enough for us to know that the electron and protons are there. So, okay, so this the mass of a atom. How do we describe the mass of an atom? since it is in the middle and all the mass are centered, concentrated at the center of an atom, all right, it is the source of the mass or the weight of an atom, all right, and it has been divided into two parts, the atomic number and mass number. The atomic number is usually described or defined by Z or Z, right? This is the number of protons in the nucleus. How many protons are there? How many protons? Proton number for certain type of atom is fixed. The proton number is never gonna change. If it is a hydrogen, there will be always on one proton. If it is a helium, there will be always two protons. If there is a carbon, there is always 6. So if nitrogen always 7, there you will never see any carbon with 7 proton. All right, you will never see any hydrogen with 2 protons. The number of protons is the identity of that atom. The identity for us is what? The thumbprint, right? My thumbprint will never match with anyone in the world. Or the passport number or IC number, it will never match with anyone in the world. So this is the identity of that proton, of that atom, the proton number. However, the electron number and neutron number can be different. All right. So just remember, proton number never gonna change for one certain. If it is 7, everywhere, anytime, it always means that it is a nitrogen. But nitrogen, although it has 7 protons, 7 neutron, it can have different numbers, 6 neutron or 8 electrons. It can vary, but proton number will never vary. Just remember that. So atomic number, the number of protons, it will never vary. But mass number, the total number of mass for protons, the neutrons, right? The number of protons and neutrons, it is the mass number, and the mass of an atom depends on this, the number of proton and neutron in the nucleus of an atom. So for carbon, as I was saying, the carbon is always having 6 proton in it. Whatever, I'm sure that you have heard about carbon 12, carbon 13, carbon 14, but all those different type of carbon, it always will have 6 proton in its nucleus. All right, the atomic number is always the same, but mass number is different, can be different. For this case is 12, sometimes it can be 13, sometimes it can be 14 as well. It depends. So in this way, if it is 12, we just deduct 6 atoms from the 12, so we know that there will be 6 protons, 6 neutrons here. We'll see in a bit. But if it is 13 and we deduct 6, then it will be 7, right? So 7 is what? 7 cannot be, proton cannot be changed. So almost, of course, there is 6 protons, so there will be 7 neutrons there. And same goes for 14. If there is 14, we deduct 6, that means the atomic number 6 or proton number 6. So there will be 8. 8 neutron will be there. So neutron number can be changed. Electron number, of course, can be changed, but proton number will never change. Just like this, that chlorine, right? Chlorine 35. And since it is 35, chlorine is always 17. The number of proton is always 17. So when there is 17 proton, if we deduct from 35, there is 18. The value is 18. So there is the neutron. It is the neutron. All right, this is neutron. And I'm coming to the electron later on, but go to here. This is chlorine as well. The same thing, because it is chlorine 100%, because the proton number is same. these two proton number are same. So it is 100% chlorine as well. But their mass number is different. This is the mass number, right? 35 and 37. Their mass number is different. And also one interesting thing is you see there is a negative charge here, and here there is no charge. It doesn't show any charge here. Is it too messy? I make it? Yeah. So you see that here is 17, here is 17 as well. Chlorine, right? Chlorine is 17. So we 100% confirm that this is chlorine because the proton number is same. But here, if we look, we see the mass number is different. When the mass number is different, what does it tell us? That if even the proton number is same, the neutron number is different for this case. And it is 20. The neutron number is 20 for this case. Another difference is, for here, I see that there is a negative charge, but there is no charge or anything here. So if it is a negative charge, what is contributing to the negative charge, do you think? Does it proton contribute to the negative charge? No, right? Because proton is positively charged. How can it contribute to the negative charge? Proton number does not increase or does not decrease. So it cannot increase, it cannot help to increase or decrease the negative charge. So what can? Electron, because electron itself is negatively charged. So if there is one more electron another thing, this is no charge on it here. There is no charge, zero charge. Is zero charge. Sometimes it is written this way to show that it is zero charge, but usually it is not shown anything. So since it is zero charge, that means it has equal number of proton and neutron, which is, proton and electron, equal number of proton and electron, because everyone is having 1 unit of charge. So 17 proton having 17 unit of proton, positive charge is balancing the 17 negative electron charge. So it should have 17 electron. Only then it can be zero charge. It should have 17 electron, and that is why it's 17 electron. But for this case, it is one charge extra, or extra negative charge, 1. That means the proton cannot balance it anymore. That proton becomes less in number. So since it has been having one more negative charge or more electron, that means it should have one more electron here. If it were 2, in this case, 2 negative, right, 2 negative, then there should be 2 excess electron than the number of proton here. All right, I hope this is clear. If we look at the periodic table here, we'll see that, for those who are, we need the refresh of the periodic table. This is how we interpret the periodic table. This is the symbol. This is the symbol. These all the symbols, right, of the element there. And then the atomic number just beneath it, the atomic number. Atomic number means the number of protons, right? And atomic weight. Beneath that is the atomic weight. That means it is the number of proton plus neutron. The proton and neutron is there. Total, because neutron is also heavy. So number of proton and electrons, neutrons are there, the sum of number of proton. So now we see that, for example, let me make it a bit bigger. For example, we see that boron is here, right? Or carbon is here, or nitrogen is here, or oxygen, right? So if 5 for boron, If it is 5, if it is If it is 5 here, oh my God. Okay. If it is 5 here, then, and there is no charge here, so that means that it should have another 5 neutron, right? Another 5 neutron. So 5 proton, 5 neutron, it should be 10. Why it is 10.8? Or for this case, is 6 proton is here, so it will be 6 proton and 6 neutrons, so it will be 12 round figure. It was supposed to be 12 and round figure, but why it's 12.01? What is the problem? Right? So this is why it is important for us to know about the average atomic weight. All right, average atomic weight, because this element occurs in the nature in different number, with different number of neutrons in its atom. Although proton is same, but neutron will be different in the atoms. All right. So some will have some boron will have with 5 neutron, some will have 6, some may have 4. So all these type, and then the percentage of those occurrence, we consider all of these things and express in an average value. And that is this 10.81 is the average value. All right, this is the average value. Same goes for the chlorine. If 17, that means it has 17 proton for the chlorine, and it should have 17 neutron, and it should make 34. It should make 34. Why it is 35.45? And it is a fraction. How does it make sense, right? So let's go and see it. Oh, I have to make it smaller. So the relative atomic mass or average atomic mass as well, we can see. All the elements in the nature, all the elements, everything that occurs with there are some isotopes there. All right. So when we see the periodic table, like how many of them you can name? Hydrogen, lithium, sodium, potassium, rubidium, cesium, scandium, titanium, vanadium, vanadium, whatever, oxygen, nitrogen, phosphorus, everything, it is having some kind of how do you call it? The twins of it in the nature, not twins, but because some of them has 10 or 15 different twins with them. It happens due to the environment, due to the different temperature, pressure, occurrence, their formulation, their occurrence, how do they occur in the nature. Due to all those things, the neutron number differs. All right, the neutron numbers differ. So that is why there are different isotopes. And when do we call it isotope? When the proton number is same, but the neutron number is different of the same element. Just like here, the chlorine, although it is an ion, but if it is like this, that one is 35, chlorine one is 37, we call them isotope of chlorine. All right, isotopes of chlorine. So the isotopes of chlorine, so isotopes of element, we have to consider as well, because that is the same thing. Only the difference, proton is the same. They will have similar property, very much similar property, almost similar property as of that element. And then we have to also consider the atomic mass of those isotopes together with this, and from there we can find the average mass. to find the average mass, this is the formula, that percentage of abundance. Percentage of abundance means one isotope, how many percent it occurs in the nature. Usually the isotopes are very small fraction, 1%, less than 1%, but still we need to consider it. All right. So 5%, I mean, 1%, 0.5%, 0.8%, all those things. So this is the percentage of abundance, atomic mass of isotope, and that isotope, this is the summation sign. So if I have 10 isotope for one single molecule element, I will have to sum it up like 5%, all right, 5%, and multiply by the atomic mass of that isotope, let's say X, and then another isotope has 0.8% times multiply by the mass of this, and it will go on like this by all this, and it is divided by the percentage of abundance. Percentage of abundance, of course, it is 100% or 1, right? Because all together, if we sum it up, it will be 1 together. Oh, here is the one example, and we can find it is very clearly that calculate the relative atomic mass of chlorine given that it's consistent of 2 isotopes. Another thing I forgot to mention, that everyone have that isotopes, some of them are not stable. Some of them they get produced either naturally or in the lab, but they do not stay. Within few seconds, they are disappeared or changes to something else. So those are not considered. At least that that will be stable in the normal temperature and pressure at the lab condition for few days. That are considered, that only those are considered in the calculation. So for chlorine, there are 2 isotopes for chlorine, 35 and 37, right? And the percentage of abundance is 79.91% and 24.01. So for 37, it is 24.91%, 75.9 is 35 for 35 chlorine. So what we'll do is, this is 35, right? According to this formula, percentage of abundance times the atomic mass of isotope. So percentage of abundance is 75.91, and the mass of this is 35, and for this is 37, and the mass of abundance is 25, and divided by the total abundance. Of course, the total abundance will be 100% always. So from here we see it is 35.5 average mass. Excuse me for a second. I think there is someone at the gate for me now. No, it was a false call. All right. So this is how we will find the percentage of average isotopic average mass, atomic mass. Now, percentage composition by mass. The percentage composition of is the proportion of individual element in molecular mass. That just now I was telling, right, that we know all that H2O, where is my pencil? H2O, there is, what is this? H2O or CH3COOH. CH3COOH, right? So H2O and CH3COOH, these are the two molecules, and this is what? Dihydroxide, isn't it? Everybody knows, right? I was just drinking it. So this is water, and this is ethanoic acid, or what the diluted version of this we call vinegar. The diluted version. Of course, do not go and drink it. Don't. So how many percent, I mean, in the molecule, we see that there are 2 hydrogen, 1 oxygen for water. In this, we see that there are 4 hydrogen, 2 carbon, 2 oxygen in the molecule. So what is the percentage of each of the element in this molecule? How many percent of oxygen is there? How many percent of hydrogen is there? Or how many percent of carbon is there? This is also important to know. When we go to, analyze, or for analytical purpose, we want to know, for example, I just want to make you feel interested that you have suddenly developed a very big, very powerful, flammable fuel, petrol type of thing, right? And of course, that type of petrol is made of chemicals. So you have to know what is the percentage of oxygen or nitrogen or hydrogen is in there, in that, of course, and carbon is there. Otherwise, you will not be able to find out the the burning characteristic of it. So that is why percentage composition is important to know as well. And it's quite simple thing, actually. The percent by mass of, for magnesium oxide is the simplest thing that we can say. The percentage mass of magnesium, right? Mass of magnesium by total mass of magnesium oxide. How many percent of magnesium is there? Times 100%. So we see that 60.3% of magnesium. So how many percent of hydrogen in water? How can we do that? Right? How can we do that? Hydrogen is, what is the mass? 1.08. 008, in fact. But it should be 2 because there are 2 hydrogen there, and divided by the total mass of water. What is the mass of molecular weight of water? 18, right? 18. 16 plus 2, 18. Times 100%. So from there, we'll see that how much small fraction of hydrogen is there in the water. Mostly it's oxygen. But it is so difficult to produce oxygen from water because if you are more interested to know more, you have to, when you go to the degree class or you study more chemistry or chemical engineering, then you'll know that it is not that easy to just dissect this hydrogen or oxygen, produce oxygen. If it were, then, because nowadays it is more than any time we need oxygen, right? It would be much easier, but it is not that easy to produce oxygen from water. So empirical and molecular formula. Empirical formula is the simplest whole number ratio of atom of different elements in the compound, and molecular formula is the whole number or actual number. Actual ratio is the molecular formula. So when I write CH3COOH, this is the molecular formula, right? This is the molecular formula. But I could also express this thing in a very simplest way, because there are two carbon here, 4 hydrogen there, and there are 2 oxygen there, right? I could also write in this way, and it would be not totally wrong. Also 100% not correct, because in this way, it all does not really always mean this thing, but this ethanoic acid we can write in this way. So this is the simplest way of writing. This is a detailed way of writing. So the simplest way of writing is the empirical formula, and molecular formula is the detailed way of writing. And empirical formula for sugar is this. There are 2 parts of hydrogen for 1 part of carbon for 1 part of oxygen in a sugar, but it does not mean that it is a sugar, right? The sugar is, there are 6, it should have 6 carbon, 12 hydrogen, and 6 oxygen atom in its molecule. Then only we call it sugar. If I give you this, nobody will drink or the tea or the juice if I add this thing in the sugar. If I say, okay, I add sugar, but my sugar, your sugar formula is CH2O. I will be scared. I don't know about you, but I will not drink, because this, although it's the empirical formula of sugar, it can mean a lot of other things, and many of the things are poison, could be poisonous, toxic. I will not drink. If you only tell me that this is you have put in my drink, only then I will drink it, because I know that this is sugar. This cannot be anything else. Okay, so example 3, I think I will stop after this example 3. My throat is paining. So calculate the empirical formula of an oxide of lead which contains 86.6% of lead. Right? 86.6% of lead, but this is a lead oxide of lead. So from there, we have to understand that this is in this formula. Sorry. This is in this formula, and both of them has the 2 valencies, so this is just fine. So if there is 66.6% of lead, then how many percentage of oxygen? Of course, out of 100%, there is only 13.4% possible for oxygen to be. Out of everything is 100%, right? So out of 100%, only 13.4% is oxygen, so 86 lead. And the lead oxide, when it is said lead oxide, you have to understand it will not be given to you the molecular weight of lead oxide. You have to find out. You should be, well versed with this thing. By the time we finish this first week lecture, you will know that how to calculate the, or how to find out the molecular weight. So lead, the molecular weight is 207, right? We just consider the mass to percentage. The percentage, since we do not have any other information, we just consider it as a gram. 86%, so 86.6% is 86.6 gram. Out of 100 gram, 86.6 gram is lead, and the rest is oxygen in gram. So what is the ratio? Gram to mole ratio. Gram over the molecular mass. So this is the ratio is 0.418, the ratio. And we have to take the simplest ratio to divide to find out the simplest possible way, so that the simplest ratio is this is the smallest. We have to divide this mole ratio by the smallest figure, smallest mole ratio among these two. And for lead, we found it is 0.418, right? For oxygen is 0.838. So we divide both by this smallest number of mole ratio. And from here, of course, if we divide 418, it will be 1. And for lead, it becomes 2. So if there is a 2 lead, there should be 1 oxygen. All right. So, sorry, if there is 1 lead, then there should be 2 oxygen. So from here, we see the empirical formula of lead oxide is lead PbO2. So this way we can find out what is the empirical formula, and from there, from the empirical formula, we can deduce the molecular or very accurate formula of this. And I will see it next class from here, relative formula by empirical formula. So I will see it in next class. I will discuss it. So our next class will be during the tutorial, the next tutorial that is coming on Thursday. And since our tutorial class has been divided into 2 groups, I will conduct the tutorial at 4 p.m. because the morning one, 8 to 10, there is only, I think, 2 students. So I hope that they can join in the afternoon. And if you cannot, then this session is always recorded. So please come and visit. You can find the link or YouTube video on the canvas. All right. So this is it for today, for now. And thank you for here. Do you have any question? Anyone?
No, sir.
Shiliang, I think just typing. No question. Erlin, thank you. Shiliang, can you talk? Is better than you talk. No question. Thank you. Thank you. All right. So thank you. Yeah.
No, I said no question.
Sorry, Munib.
I said no question, teacher.
Okay. All right. So if you have any question, doesn't have to be related to this topic. It can be to other topic. You can ask anytime, and you don't have to wait till I stop.